Hello students, good morning and most welcome in the chemistry class. Students, we are doing the chapter D and F block elements. I think you have done your assigned work because I have seen many students submitted your assigned work. My dear children, today's topic on the chapter D and F block elements, trends in stability of higher oxidation states. Higher oxidation states. Stability. We have to discuss the stability of the compound with fluorine and oxygen. Fluorine and oxygen. You know that fluorine is the most electronegative element and its electronegativity value is 4.0, and second highest electronegative element is oxygen, that is 3.8. The ability of fluorine to stabilize the highest oxidation state is due to either high lattice energy, as in case of COF3 cobalt fluoride, or high bond enthalpy in the case of VF5 and chromium hexafluoride, that is CrF6. So what is I am telling here? The ability of fluorine to stabilize the highest oxidation state is due to either high lattice energy, as in case of COF3, or high bond enthalpy, as in case of VF5 and CrF6. The ability of oxygen to stabilize the highest oxidation state is due to its ability to form multiple bonds with metal. So, what is the factor that is responsible for the ability of fluorine to stabilize the highest oxidation state? It is either high lattice energy or it is either high bond enthalpy. So, high lattice energy or high bond enthalpy are responsible for the ability of fluorine to stabilize the highest oxidation state. But in case of oxygen, the ability of oxygen to stabilize the highest oxidation state is the multiple bond formation of the oxygen with the metals, p-pi bond formation. Stable halides of first transition elements in the oxidation state +6, that is chromium F6, +5 VF5 and chromium pentafluoride, +4 TiX4 and MnF4. In +3 state, TiX3, titanium X3, vanadium X3, chromium X3, manganese F3, iron X3 and cobalt F3. +2 state, titanium X2, vanadium X2, chromium X2, manganese X2, iron X2, cobalt X2, nickel X2, copper X2 and zinc X2, and +1 state, that is copper X. X equal to fluorine to iodine. What is X? You know that halogen family. Halogen family fluorine to iodine, and X dash fluorine to bromine. X double dash, that is X double dash is equal to fluorine, and X triple here denotes, that is chlorine. Chlorine to iodine. Chlorine to iodine, my dear children. So these are the stable halides of the first transition series. Suppose in the exam there is the question, name the stable halide of the first transition series. Student, can you tell me which series is known as the first transition series? Yes, your answer is absolutely right. The 3D transition series is known as the first transition series, and it belongs to 10 elements, that is scandium to zinc. Scandium atomic number 21 and zinc atomic number 30. So total 10 elements present in this series. So in this series, the stable halides examples, that is CrF5, CrF6, VF5, COF3, MnF3, etc. So first of all, stable halides of the 3D transition series I have explained. You have to note down in your copy, students. The highest oxidation numbers are achieved in titanium tetrahalides, VF5 and CrF6. The plus 7 states for manganese is not represented in simple halides, but MnO3F is known, and beyond manganese, no metal has a trihalide except FeX3 and COF3, my dear students. Although vanadium is represented only by V5, the other halides, however, undergo hydrolysis to give oxohalides, VOX3 oxohalides. Another feature of fluoride is the stability in the low oxidation state, as for example VCl2, VBr2, Vi2. That is low oxidation state, the fluoride is the instability. In the low oxidation state, the fluorides are unstable. So these are the tetrahalides of titanium, pentahalides of vanadium, and hexahalides of chromium. The highest oxidation state are achieved in TiX4, VF5 and CrF6. The plus 7 state for manganese is not represented in the simple halide, but MnO3F is known, and beyond manganese no metal has a trihalide except FeX3 and COF3, my dear students. So you have to know the stability of the halides of the 3D series elements. This is very important things here, students. All copper in the plus oxidation states, halides are known except the iodide. In this case, copper 2 plus oxidizes iodide to iodine. So questions will come, halides of copper are known. Halides of copper are known except the iodide. Give reason. You have to give the reaction here. That is copper in the state of plus 2, when reacts with iodide, then copper 2 plus oxidizes iodide to iodine. In iodide, the oxidation number is -1, but in iodine, oxidation number is 0. So -1 is increased to 0. So iodide is oxidized here. It is the reducing agent, and copper is the oxidizing agent. It reduces itself. But iodide is oxidizes to iodine. That's why copper iodide, in the copper in the plus 2 state, copper iodide is not known, but other halides of copper 2 is known. However, many copper in the state of one compounds are unstable in aqueous solution and undergoes disproportionation reaction. This question is very, very important, students. Every year we see this question is coming. Why copper 1 plus compounds are unstable in aqueous solution? So copper 2 plus, when undergoes in the aqueous solution, it produces two compounds, Cu2 plus and Cu copper in the zero oxidation state. The stability of copper 2 plus rather than copper plus is due to much more negative del H hydration, that is the hydration enthalpy. A copper plus is much more negative of Cu2 plus than Cu plus. So what is the answer? Why copper 2 plus is more stable than copper plus 1 in the aqueous solution? The answer is number 1, much more negative del H hydration of Cu2 plus than Cu plus, and which more than compensates for the second ionization enthalpy of copper. Copper first undergoes, that is copper loses 1 electron from the copper plus 1. Again copper plus 1 loses 1 electron and forms copper 2 plus. And del H hydration, negative del H hydration's value of copper 2 plus is more, and which more than compensates for the second ionization enthalpy. So here ionization enthalpy and hydration enthalpy value you have to write. That is more negative hydration enthalpy, which more than compensates for the second ionization enthalpy of copper. So this is the answer. Why copper 2 plus is more stable than copper plus 1. So these questions you have to write in the notebook and learn it. Practice more and more these questions, students. Transition metals also exhibit the highest oxidation state in their oxides. Highest oxidation state in their oxides. The ability of oxygen to stabilize higher oxidation state are much higher than fluorine. The highest oxidation state with fluorine by manganese is +4 in Mn4, while it is +7 in Mn2O7. In manganese, oxygen, you know that oxidation state -2. So 7 oxygen -14 and 2 manganese +14. So 1 manganese +7. So what is the oxidation state of manganese in the compound Mn2O7? Tell me, students. Yes, your answer is right. The right answer is the +7. So Mn2O7 in this compound, the oxidation state of manganese is +7. Oxygen has the ability to form multiple bonds with metal atom. Already I have discussed about this. The oxides of 3D transition elements are given below. So transition metals also exhibit the highest oxidation state in their oxides. They show the highest oxidation state in their fluorides or halides. They show the highest oxidation state in the oxides. Now, these are the oxides of the 3D series. Already you have seen the halides of the 3D series. Now, you have seen the oxides of the 3D series, like as Mn2O7, where manganese exhibit the +7 oxidation state. CrO3, chromium exhibit the +6 oxidation state. So in this manner, there are many oxides of 3D series, V2O5, MnO2, in the +4 state TiO2, V2O4, CrO2, etc. In the +2 state TiO, VO, CrO, MnO, FeO. So many oxides in the +2 states, and +1 state only one oxide is there, that is Cu2O. It is known as the cuprous oxide, and CuO is the cupric oxide. In +2 state, cupric oxide. In +1 state, cuprous oxide. So these are the oxides of the 3D series. Now, highest oxidation number in the oxides coincides the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of iron above Fe2O3 are known, although ferrites in the oxidation state 6 are formed in alkaline medium, but they readily decomposes to Fe2O3 and O2. Beside the oxides, oxocation stabilizes, that is vanadium as VO2 plus, vanadium in the 4th state as VO2 plus, and titanium TiO2 plus. So these are the oxides of the 3D series. These are the oxides of the 3D series. You have to learn, students, the oxides of manganese, where the oxidation state of manganese is +7, that is Mn2O7. Mn2O7, highest oxidation state. Mn2O7, that is manganese, exhibit +7 oxidation state. One question is coming in the exam. Frequently we are seeing that which element in the 3D series exhibit the maximum oxidation numbers? The answer will be manganese. Answer will be manganese. Now, students, standard electrode potential. We have discussed the halides, oxides of the 3D series. Now, the standard electrode potential of the 3D series element. Electrode potential are the measure of the value of total enthalpy change. What is electrode potential? It is the measure of the value of total enthalpy change. Total enthalpy change. Electrode potential value depends enthalpy of atomization and hydration. Enthalpy of atomization and enthalpy of hydration. The electrode potential depends upon the two factors. Tell me, students, which factor? First factor is enthalpy of atomization, and second factor is enthalpy of hydration. Very good. Lower the standard electrode potential, the more stable is the oxidation state of the metal in aqueous state. I am telling here, oxidation state, lower the electrode potential lower. It means the more stable is the oxidation state of the metal in the aqueous solution. So electrode potential, what is electrode potential? It measures the value of total enthalpy change. Okay. Number 2, electrode potential value depends enthalpy of hydration and enthalpy of atomization. Number 3, lower the electrode potential, it means the more stable is the oxidation state of the metal in the aqueous solution. So electrode potential value lower, it means the stable oxidation state. For the first row, transition metals, the E0 values are given. E0 values of vanadium, chromium, manganese, iron, cobalt, nickel. Explain the irregularity in the above values. Just you have seen vanadium minus 1.18, chromium minus 0.91, whereas manganese again minus 1.18. There is the irregularity. Iron minus 0.44, cobalt minus 0.28, nickel minus 0.25. But very interesting, one question is coming, why the reduction potential of copper is positive and others element reduction potential is negative, only copper has the positive. The E0 values are not regular, which can be explained from the irregular variation of ionization enthalpies, and also the sublimation enthalpies, which are relatively much less for manganese and vanadium. So two factors are related here, that is ionization enthalpies irregular variation and the sublimation enthalpy irregular variation. Ionization enthalpies and sublimation enthalpies. Students, you know, first the metals in the solid state converts in the gaseous state and sublimation enthalpies are required. And again, the gaseous ions, when release electrons, it forms the positive ions, and here is the ionization enthalpies related. So irregular variations of the ionization enthalpies and sublimation enthalpies, which are responsible for the irregular reduction potential of the 3D series. So two enthalpies are related here. So this is about the copper value. Copper is positive, high hydration enthalpy, high atomization enthalpies, and low hydration enthalpies. Greater amount of energy required to transform Cu into Cu2 plus, Cu into Cu2 plus. The high atomization enthalpy and low hydration enthalpy. It means that greater amount of energy required to transform copper into copper 2 plus, copper into copper 2 plus. Due to positive E0, copper does not liberate hydrogen from acid. So questions will come. Why copper does not liberate hydrogen from acid? Answer, because it has positive electrode potential and the value is plus 0.34 volt. Positive electrode potential. The general trend towards less negative E0 values across the series is related to the general increase in the sum of the first and second ionization enthalpies. It is interesting to note that the value of E0 for manganese, nickel, and zinc are more negative than expected from the trend. The stability of the half-filled D subcell in Mn2 plus and the completely filled D0 configuration in Zn2 plus are related to their E0 values, whereas E0 for nickel is related to the highest negative del H0 hydration. The low value for scandium reflects the stability of scandium 3 plus. And scandium 3 plus, it means the inert gas configuration, which has a noble gas configuration. In case of zinc, D10 configuration completely filled d orbital. The comparatively high value for manganese shows that Mn2 plus is particularly stable, whereas comparatively low value for Fe shows the extra stability of Fe3 plus, that is D5. Students, you know that D5, D10 configuration, stable configuration, and inert gas configuration, stable configuration. The stability of the half-filled d subshell in Mn2 plus and the completely filled d orbitals, that is Zn2 plus, are related to their inert values, whereas inert for nickel is related to the highest negative del H, that is hydration enthalpy, highest negative. So students, up to this, that is the halides, oxides of the 3D series today we have discussed. Next we have discussed the electrode potential, standard electrode potential. Very important things. Many questions coming from the standard electrode potential and the half-filled and full-filled orbitals, D5, D10 configurations, that is Mn2 plus and Zn2 plus, very stable configuration, Mn2 plus D5 and Zn2 plus D10 configuration, and this is related to their inert values. Okay students, up to this, next day we will discuss the chemical reactivity of the 3D series elements. Chemical reactivity of 3D series elements. Thank you students. Today up to this, and be safe, be healthy, stay home.